Good morning. The only announcement I have is about your final lab, lab number 5. It's going to be a relatively shorter lab for sure, given that we only got some days left, but we can definitely take advantage of some days before the end of the semester. Lab number 5 is going to be about recursion, which we're going to start and also giving you enough details by the end of Wednesday's lecture. So you definitely are ready. You will be ready to complete the lab. And that's also going to help you prepare for the final exam, which also covers recursion. Make sure you're properly prepared. Okay? That'll be lab number 5. You can expect it to be released by the end of Wednesday. All right. Okay. So seems to be okay. And we are basically done with the inheritance lecture. It took us about 6 lectures actually to finish it, which is good because we really covered that thoroughly. I would like to talk about just 2 more things. Nothing new, but just to maybe reaffirm your understanding. Number 1, okay? This one was inspired by some discussion with Marcus after class about 2 weeks ago, okay? I'm gonna give you guys some idea about what you should really think about, and then we'll talk about this example. It's also actually very useful, given that you have written test number 3 tomorrow. Let's say we got class A, and also we got class B and C, right? Of course, once you have seen this inheritance hierarchy, you can draw the diagram right away. Class A at the top, and also we got 2 extents, B and C, right away. And notice one more thing. There is only one method which we assume has been declared in the superclass M1. And you can see here, I simply got empty, meaning that these 2 classes will simply inherit M1 verbatim. As far as the range of expected methods you can call on A and B and C, you want to think about what that would be, right? That's really the purpose of this example. Let's now take a look. I want you guys just to think about number 1 over here, and also number 2 over here. Let's start with number 1. For number 1, do you think it is going to compile? Okay, if you guys say no, that's very good, because at this point, it should be mechanical. However, I'm going to make some arguments to see if I can change your mind. Okay, number 1, this variable assignment here is not going to compile, because the dynamic type that we are trying to initialize over here, A, is not a descendant of the static type of obj1, which is B. Right? You can see A here is not a descendant of B. It should be the other way around. Another way to put it, which is the intuitive way, argument number 1 and number 2. A cannot fulfill the expectations of B. Right? You can see A here cannot fulfill B. A cannot fulfill B. A can only do that if A was a descendant class of B, right? That's basically what we got so far, okay? All right, that's basically what we have talked about. However, I'm going to make some arguments, and please listen to that carefully, okay, to see if it might change your mind. We say that the reason that this variable assignment is not going to compile because A here cannot fulfill the expectation of B. But in this particular example, why not? Because you can see A has only the expected method N1. B and C both inherit this method here without overriding them. And also, there's no new method in B and C. So we may argue that the expected or the supported method for both A and B and C are exactly identical. So shouldn't we actually allow this variable assignment in the first place? That's my question. I'll write it down. So if you look at here, at the moment, no new methods have been introduced. This means B and C and A have just identical expectation. All right? It might sound like a contradiction, but that's exactly the point I'm trying to make over here. Okay? Anybody will change your mind. Before I point to Marcus, because I already spoke to him after the class. He knows the answer. Okay, Ferris, would you like to try? So just tell me one thing. Given the discussion I just had, would you say this variable assignment here should be valid instead, rather than invalid?
We actually said that, I think Eclipse itself just to check if B extends A and it doesn't check every method procedure.
Aha. Okay. Yeah, so that means you wouldn't change your answer. Okay, very good. So Ferris actually just said is actually exactly correct. What Eclipse does, as far as compilation is concerned, it doesn't care about what methods you actually have got so far. You only check to see if you want to do this variable assignment, does A extends B, for example? It doesn't. So that's why you wouldn't compile. So keep that rules. And this argument over here, I want you guys to think a little bit more carefully, because this is a common confusion which Marcus presented to me after class. At the moment, even though there are no new methods in these two subclasses, but you cannot deny in the future there might be some new methods introduced into these classes, because your project is always subject to changes or evolution. All right? So that's why this remains to be invalid in case you have that confusion before. Okay? And then, so in the future, new methods are anticipated. Okay? And it would be a similar idea over here. So if you think about this particular line, okay? OBJ2 over here has the static type A. When we try to cast A to B over here, from A to B, it's a downward cast, which is okay, it compiles. However, are we going to run into class cast exception? That's the question, right? That's also something you should know for tomorrow. Okay, it's a downward cast. Number one. Number two, but do we have class cast exception? Anybody? Do we or do we not? And how do you judge if there will be a class cast exception? Marcus, would you like to try for us?
I don't remember this words, but if the dynamic type cannot fill cast type, so
absolutely.
the dynamic type is A, the cast type is B.
In this case, we're right into class cast exception. Can A, the dynamic type, fulfill the cast type B?
No.
Mm-hmm.
Like as of now, technically yes, but in general, no.
Exactly the point. So we only talk about in general. At the moment, sometimes it doesn't really quite matter, because in the future, they might just change. All right? So this part over here, we're going to run into class cast exception, okay? So this part over here, there will be class cast exception, because the dynamic type of OBJ2, at the moment, it is A. Cannot fulfill the expectation of the cast type. If you think about this is, if you look at these two types, right? You can see the A here is the dynamic type of OBJ2. And the B here is what you want to cast that to be, cast type. You will only be cast exception free if the current dynamic type can fulfill its the cast type, meaning that it must be an ancestor. Sorry, the dynamic type must be a descendant class of the cast type, but it's not the case, right? Class cast exception. So for tomorrow, let me give you a tip. You will be given some Java decorations like this. Of course, you're going to bring your sketch paper and sketch. You will be asked the various questions that we have done so much, up to now. So whether things compile, and whether a cast compile, for example, and also if a cast compile, would it write into class cast exception, right? You will see that in the practice question. And definitely on the exam as well. All right, any point you would like me to review? Well, you guys are okay. Okay. All right, I presume everybody is fine. And there's one more slide that you will see on the inheritance lecture. Okay, this one here. This one here looks a bit terrifying because it's completely symbolic, right? I will help you a little bit on one row. This one here really is very valuable. It summarizes everything that we have learned in the inheritance lecture. Let's just do one of them. Okay, I'll do the most complicated one together with you to give you some hints. Let's now do this one here. This one over here is asking, in order for this particular method call, you can see context objects, dot notation, some method, and this is some arguments. And for the argument, we have some cast expression, which we definitely talk about, right, in the lecture. Okay? Now the question is, under what circumstances precisely is this line going to compile? There are several things you actually want to watch out for. Okay? I'm going to outline what you want to watch out for. Number one, you want to make sure this call is actually valid. Number one. Okay? And also, you want to make sure, number two, this particular cast is also valid. And number three, you want to make sure once the cast being valid, can it be passed as argument into this particular method M, right? We talk about polymorphic method parameters. So this part over here will be number three. So these are the three issues you want to deal with, right? You can definitely see the precise conditions over here, which we also talked about in the lecture before. Let me just hand wave a little bit. How can this method call be valid? It is when the static type of the context object X actually define this particular method. Otherwise, how can you call that method, right? For example, if you call BMI, get BMI method, then the context object over here must be a person class. It cannot be, for example, like a vaccine class, right? It wouldn't make sense. That's number one. Number two, in order for this cast expression to be valid, it should be either upward or downward casting, right? And also, given that it compiles, are we going to write into class cast exception? And we also just review the condition. Given that this cast expression compiles, how can you pass this as argument into this particular method? In that case, you want to review about call by value, right? In which case, you're going to have parameter is assigned to the arguments. And you want to make sure this particular variable assignment is actually valid, right? That's also something we spoke about very thoroughly in the lecture, right? Okay, it's just a guidance about how you can read this particular table. This is the most sophisticated one. Other ones are actually simpler. Okay. All right, any question about this? We okay? Right? You still have more than 1 day before the written test, and definitely a few about more than, I think about 2 weeks or so before the exam. Definitely make sure you master these concepts. They will definitely be covered to assess. All right. All right, so can I leave you guys alone with this? If you got questions, drop by, office hour. Okay. Let's now move on to a new topic, okay? This will be the last topic for the course, recursion. You may have seen maybe recursion back in your first year courses, but I wouldn't assume any background on that because sometimes some instructor maybe wouldn't get a chance to cover recursion in the first year, just to be equal to everybody, so I will start from scratch about recursion. Let's not try to be too ambitious for this course since we only got 3 lectures and also 1 lab to help you understand recursion. I will focus on the very basics about recursion, just make sure you understand the basics, and we're going to do some very specific pattern of recursion also to help you understand how to get things done. Recursion is actually a very tricky topic. I can tell you many CS or engineering graduates, even when they graduate, they wouldn't necessarily know how to program recursion properly. You just need to practice, practice, practice. I will give you some tips right away in the slides, but that will be beyond this course. You can definitely try to do them if you're interested. But recursion is definitely very important for any more advanced course. For example, 2011, in the new semester in the winter, you definitely need recursion to do things like trees, right? Question? We don't really cover backtracking here. No, that would be a little bit too advanced at this point. So I'll rather maybe cover just about some very simple recursion and then to see how we can trace them using the stack, and also some simple ones you can do creatively, not backtracking. Yeah, okay. All right, for recursion, let's see. Yeah, how to solve problems recursively in general. I'm going to give you some high-level idea, and also example recursion. I will start with some recursion on just Java string, okay? And also we're going to do maybe on Wednesday on recursion on arrays by manipulating the indices and also call by value. That's something we'll do. And some more advanced example we'll see if we really got time. Maybe I can show you one or two. We'll see. Most likely if we have time, it will be next Monday, the last class. Okay, let me tell you the tips right away. So these are the two sites I will highly recommend you go there, actually try. They are of the style like a leak code, like an interview website. If you go there, they actually got, I'll just show you some of them. If you actually go there, and then you will see they got Java, not Python, Java. You can see recursion 1. So this will be the more basic example. Factorial we're going to talk about today, and also many others. If you click on any one of them, it's going to show you just empty method header, pretty much like a lab test environments. I would suggest try as many examples as possible for your understanding. Okay, we definitely cannot cover every one of them. Okay, I'm going to cover just enough so you will be able to do them on your own. Okay, that'll be the plan. And another tip, definitely it will be only up to those of you who can afford the time, and also if you're curious. The best approach to learn about recursion is to learn about a particular programming language paradigm called functional programming language. Very briefly, Java or C, which you will learn in your curriculum, in your degree, they are more like a procedural language. You can definitely program in recursion, but they don't really occur that often. Okay? However, if you try to program in some functional programming language, in that case, you have to do recursion all the time. So in order for you to really survive in writing programs in functional programming language, you have to do recursion all the time. I included a link over here. It's a very popular functional programming language called Haskell. If you are interested, go ahead. That would be something to invest your time, maybe over the break. Okay? Just for your information. Okay, so let's talk about some principle, and then we'll do two typical hello world examples for recursion, and then we'll take a break. Okay? Principle. Recursion is very useful in expressing solution to problems that can be solved recursively. But what does it really mean to solve problems recursively? Let's understand the high-level idea. We got base cases. What does it really mean to have base cases? That means cases where you can solve the problems right away without hesitating. Just like that. Just immediately solvable. There will be another category of cases called recursive cases. What do they mean? Recursive cases simply mean I cannot really solve this bigger problem right away. I need to divide the problems into smaller problems, solve them individually, and then combine the smaller solution together into the bigger solution. That's the recursive cases. And based on how I described, you might find some similarity to mathematical induction that you learned from the high school. Very quickly, I don't want to bother you too much with the math. Mathematical induction, how do you prove? Let's say you want to prove some property about natural number, starting from 0 all the way to plus infinity. You try to prove some small cases, maybe when I is equal to 0, I is equal to 1, and then you assume you have I, which is equal to maybe some k. And then you try to use that to prove I is equal to k plus 1, and you can prove everything. It's a very similar pattern you will see in recursion, except that we're going to do everything in the programming context. Okay, that's something we'll do. Good. All right, so recursion can be, well, when I say easily, I mean once you know how to solve that conceptually, it will be quite easily to translate into Java. So let me show you something here. Based on what I just have said, let me show you some very conceptual sketch, and then we'll get into some example. So always remember, to solve a problem recursively, you got two cases, base case and recursive case. So this part over here will be the base. And this part over here will be the recursive case. In the base case, you're given a problem that is very small. You can provide its solution right away. Okay? In the case of recursive case, you're given a very much bigger problem over here, which you cannot solve right away. How do you solve it recursively? First of all, you know how to divide this bigger problem into smaller problems individually. Each one of them turned out to be something like a base cases themselves. And then try to solve them, getting some smaller solution, and then try to combine them into a bigger solution. So to really go from here to here, you need the intermediate stages to divide and concur. Okay? That's really the big idea. For every recursion example we're going to see in this course, and also in any other context, this will be the general pattern. When the problem is too big for you to solve right away, you have to divide the problem into smaller ones. Solve them individually, combine them to get the solution for the original big problem. That's really the key. If you always remember that principle, just reaffirm, reaffirm, reaffirm. Okay. One more thing to say about Java. How do you tell if you're having a recursive method? Basically, whenever you have some method here, let's say m, with some parameter, parameter I, and then inside this method here, you find that it's calling itself. Most likely, you're having a recursion. Okay? But there will be one thing that's also very important. You can see m here is basically calling itself with some arguments over here. Okay? This basically corresponds to if I want to solve this particular problem over here, instead I'm going to solve maybe a smaller problem. You can think about this part is more like an I. That's about the size of the problem. In order to solve the problem of a very big size I can try to solve a smaller size j, smaller size k, and smaller size l instead. Right? So you can see, think about the j here and I here. Okay? J here and I here. And very critical to remember, whenever you try to make a recursive call, the j here must be strictly smaller than I, meaning that solving a strictly smaller problem. So far, we are not talking about any programming just yet, but recursion itself is also a mathematical concept. Just get this concept straight. Okay? Let me recap, and then we'll move on. Whenever you want to do recursion in Java, let's say, of course, you got to declare some method. Inside the context of the method implementation, you might call itself for as many times as you like. Here, I'm just showing one time. It could be multiple times. But notice that every time you're making a recursive call, the argument over here conceptually must be a strictly smaller problem compared with the original one. If you try anything that's maybe of the same size, then you will run into infinite recursion, which I'll show you some example. It's a very common error. Okay? That'll be the general idea. If you got the idea, that's a really good first step. Okay? Okay? And this slide here, good news, you have seen that already before. So basically, how can you trace the method call using a stack? If you just go back to the very, very early stage of the course, about when we introduced the idea about exception, we talk about caller, callee, and the call stack. That's exactly a review on that particular concept. So for this slide here, I'll let you read it. Nothing is new. You just have to remember you have to use the so-called a stack to trace the method call. That's something we'll do also today. I'm going to do 2 examples today, okay, just to make sure you're fine. Okay, so the first problem that people always talk about when they introduce recursion is a factorial example. Okay, why don't we talk about it? And just to remind you, that's the factorial, right? I'm pretty sure you know what factorial is, but it doesn't hurt to revisit its definition. And then I'll try to lead you a little bit of how to think recursively. Okay? So what's the definition for n factorial? If we say 1 factorial, if we say 0 factorial, it would just be 1. It looks like a base case. Because when the n here is simply just 0. The problem is very trivial. You can solve it right away by just returning 1. Okay? So you can think about this part here is more like a base case or simple case. This part over here, I have a quick question for you. Do you think this part over here is a recursion? Okay, I'll just put the question here. Is this recursive? In order to see if this particular definition here is recursive or not, you have to see. This is the problem that we are trying to solve. Whatever n we pass over here, we want to calculate its factorial. So this is the problem. Now, in order to handle the case where n is larger than or equal to 1, are we mentioning about anything's factorial anymore? Are we? Not really. We just say n multiply n minus 1, n minus 2, all the way to 1. We are not really talking about maybe n minus 1 factorial. We're not talking about it. So it's not really recursive. Okay? It might take some time for you to digest, but I'll write down the points you need to know, and you can review them later. No. Because the problem, which is about factorial, is not reduced into smaller problems in the definition, right? The definition over here. You can see we only got n minus 1, n minus 2, all the way to 1. We don't really have, maybe, for example, n minus 2 factorial. We don't, right? That's why it's not recursive. In order to really program this in Java recursively, let's now think about how we can convert this solution here that's non-recursive into recursive. That's what we want to do, okay? So we want to have a recursive solution. And always remember, if you want to program something recursively, think about base cases. So for base cases, in here we just got one case. When n is equal to 0, just 1. Okay? So 0 factorial is going to give you 1. Base case, easy. Okay? What about recursive case? If I want to calculate n factorial, so now this part over here is something we have to work out. Okay? So this part here, we want to write it in a way different from this. We want to write it in a way that this can be equal to maybe the solution to some problem of factorial manipulated with something else. That's what we want to do. Okay? Is it possible to break down the factorial calculation into maybe the factorial of something else before we actually calculate the final result? Is it possible? Based on this definition. Yes. Is it possible to calculate the factorial over here in a way that rather than just calculating n minus 1, n minus 2, is it possible to say, I want to get a solution of a smaller factorial and then do something slightly more with it? Is it possible? I'll give you guys one visual hint. Look at here. What I did was I tried to separate the original solution over here, which is not recursive, into two parts. One part is over here. The other part is over here. What's this part? Yeah, I agree. It's a factorial of n minus 1. So guys, maybe it's just the way I phrased the problem. Maybe it's not so clear to you. But just notice that what I highlighted here, n minus 1 factorial. Because we start from n minus 1 and go all the way down to 1 with multiplication. If we start with n, then we go all the way to 1. So that'll be n factorial. So now see this. n minus 1 factorial over here is part of the solution. If I can get this somehow magically, I will be just able to multiply that solution there by n. Okay, I'll put it down, and then I'll just give you a little bit more remark. So that'll be n minus 1 factorial multiplied by n. Okay, so what can we conclude? In order to solve this problem over here, which I cannot do right away, I can try to say, let me assume I got a solution for a strictly smaller problem. If I got it, I can just multiply its answer by n. Okay, that's the idea. I can tell you the most tricky part about recursion is this part. You might be asking, how can I assume there's such a solution here magically? How is that possible? Okay, we'll see. Okay, I'm going to put it here. So you can think about this is the solution to a strictly smaller problem. And this will be some extra stuff you can do to really get a bigger solution, right? Remember remember what we had before. Let's think about this diagram here. We wanted to solve n factorial. In order to do it, we try to break it down into maybe just n minus 1 factorial. Just n minus 1 size. You can see we reduce the size from n down to n minus 1. Once we get a solution for n minus 1 factorial, we can do something with it to get a final solution. In this case, we just say n multiplied by n minus 1 factorial. That's kind of the step. And every recursion method you're going to program, either easy or hard, will more or less follow this pattern here. Right? We'll just need to do more example. Okay, so this will be the final recursive program design we're going to follow. N factorial will be this one here. If n is larger than or equal to 1, that's a recursive case, and this will be the base case. Right? Now we want to translate this into Java. Okay. And what I showed to you is just one way to translate it, right? You can feel free to try different way. That's possible if you want to, right? Here, I just try to have some integer result and try to assign that to something and return the result. And some other people maybe wouldn't want to have the intermediate local variable. That's fine too, right? I'll leave that to you. Let's take a look. You can now try to see n factorial is corresponding to factorial method with parameter n. And then over here, you can see the n here is corresponding to the n here. And the n minus 1 factorial over here is a recursive call to factorial of n minus 1. Okay? One more. The 1 here is here. When n is equal to 0, in that case, you just return 1. So 1 here. Okay? That's showing the exact correspondence between the two. Okay? This is how you can think conceptually or mathematically. This is what you have to program in Java. Okay? Can I just have you stare at this Java code just for 1 minute, and then we'll try to trace it using a call stack. So this will be a simple example. We're going to do something a little bit more complicated after this. Okay? Just stare at that for 1 minute. Okay? And then we'll try to trace it. Okay. Okay, just one more moment, and then we'll start tracing it. And the example we're going to use will be factorial 3, which is rather simple. Okay, and to make it clean, why don't I just start with a clean page over here? And I'm just going to wipe out the highlight. Okay. Okay, let's try to trace. So what we want to trace is this one. Factorial 3. As soon as we want to execute this, maybe from the main method, or maybe from some JUnits method, doesn't matter. Let's say that's what we want to trace. You should really push that onto the stack right away. And I'm just going to write in short, just fact, okay, rather than factorial. Factorial 3, that's the method we're currently executing, right? The way I'm going to trace this is similar to how we trace it for callee in the earlier lecture. So this part here is actually just reviewing. Okay, let's say we want to do factorial 3. So what we do is we're going to call this method over here, and the n is going to be 3. Okay, and then which case are we going to satisfy? There's only one, either the base case or the recursive case. Apparently, n is not equal to 0. Agree? So definitely we'll go here. Okay, that one's good. So what we're going to do is we're going to go to this line over here. Okay, we're going to calculate 3 multiply the factorial of 3 minus 1, which will be 2. Are we okay so far? That means in order to finish the execution of this, we need to calculate the multiplication of 3 times this. But for this guy here, we need to calculate it first before we can get back to the multiplication. So that means we're going to get another factorial calculation in the stack. That's the essence of tracing recursion on the call stack. All right? So we're going to push factorial 2 onto the stack. Okay? In order to trace this, let's now use a different color. So we're going to trace this one here. So now rather than 3, used to be 3, it's now 2. Right? Oh, let me let me do it again. It's going to be 2. Oh, that's fine. Beg your pardon. Okay? And then it's going to be 2. Okay? And then we're actually going to method once more. Are we going to recursive case? What you want to ask yourself is this value here small enough so that we can return the result right away? Not yet. Right? 2 is not equal to 0. So we're going to go to the else part over here. So we're going to calculate this once more. And what should we do? So here we're going to say 2 multiplied by factorial of 2 minus 1, which will be 1. So far so good? Okay. And we cannot really evaluate this until we actually finish this. Okay. So that means we're going to push factorial 1 onto the stack right now. Okay, we're going to calculate it. And when we try to calculate factorial 1 over here, so now we're going to calculate when n is equal to 1. Okay, question. Is 1 here small enough for us to return right away? Well, is it satisfying this? No. So that means we're going to go for recursive case still once more. As far as the base case size is concerned, this is still too large because it's not reaching 0. Only when we reach 0 are we going to actually continue with the base case execution. Over here. So let's do it again. So we're going to have, so this will be 1. So 1 multiplied by factorial of 1 minus 1, right, will be 0. And that means before we can calculate this particular multiplication, we have to calculate factorial 0. And one thing to note, you can see in order to trace the recursion, before we can reach the base case, the stack is keep growing. So should we grow the stack indefinitely in general? We shouldn't. At the point that we reach the base case, that means the call stack is going to stop growing, and then we keep popping until we actually get a result. That's a very important observation. I'll write it down here, and then we'll see how we can calculate down from the base case. In order for the call stack not to grow indefinitely, we need to make sure that the base case is reached ultimately. Okay. A very common mistake is you never reach the base case. Okay, we'll see that example. All right, so let's now calculate this once more. Factorial 0. So when we try to calculate factorial for the fourth time, so it's going to be 0 over here. And indeed, this time we're going to reach this base case. And then we're going to return just 1. Right? Result is actually 1. What does that mean? That means we are able to replace this particular part just by 1. Also, it corresponds to we actually pop this method off the stack. Right? It's going to be 1. And this is the calculation that we didn't really do. Now we are able to do it. So it will be 1 multiplied by the factorial of 0, which is 1. So this one is going to give us just 1. Okay? So this will be the result for factorial 1. Okay? And once you got a factorial 1 result, we just keep popping. Once you get a factorial 1 result, it's actually going to be 1. And this part here is also going to be 1. Right? And then you try to do this calculation over here. It's actually going to be 2 times 1. It's going to be 2. And what will be this result? This one here is just corresponding to factorial 2, which is 2. Okay? We just keep popping off the stack and get a result. And the final one is this one here. We know that factorial 2 is this result 2. And then we try to calculate 3 times 2. This is going to give us 6. 6 is going to correspond to this result. So eventually, the 6 will be what's going to be returned. Okay. Let's now try a slightly different way to visualize what's happening here. Tracing the cost stack is a bit tedious. I'm going to do one more, but we can leave you alone with other parts. Think about what's happening here. We start with factorial 3. In order to calculate it, we have to calculate 3 multiplied by factorial 2. In order to calculate, you know what? Let me just get a larger one. Okay, let's see this. We wanted to calculate factorial 3. In order to do that, we have to calculate 3 times factorial 2. And in order to calculate this, we have to do 2 times factorial 1. In order to do this, we have to calculate 1 times factorial 0. Okay? So I think that this way here might be easier for you to see the big picture. But of course, you should know the corresponding stack as well. And this will be the base case that we just reached. Okay, so this will be the base case. So once this is returned, we know factorial 0 is 1. And then this part over here is going to be 1 times 1 is going to be 1. So that means this part over here is 1. And then we try to calculate 2 times 1 over here is going to give us 2. That means this part here can be replaced by 2. And then this part over here, 3 times 2 is 6. That means this result here will be 6. This will be the final result. And this is much quicker and maybe much more straightforward. But it does correspond to what we just traced in the cost stack. Right? You should know both. Okay. Are we okay with this? Or any part you actually got trouble understanding? We okay? Okay. So this is really important to actually get, just for the first example. We got one more. Okay. Before I do that, why don't we take a break and take attendance, and then we'll get back to recursion. All right? Yeah, just bear with me. I got to refresh my location. 30, and then okay, and then let me see settings, attendance, don't require, allowed, save. Okay, good. Okay, let me just start a class. And you should be able to now check in. Okay, go ahead. Everyone's okay to check in? Everybody? I'm going to stop it. You're not able to?
Okay, sorry. I came in a little late, so I don't know where to get the iClicker code.
No, you just need to, have you signed into the class? That's what you got to do. Okay. Come to the front and then show me your student ID, and then I can check you in, okay, in the sheets. Yeah, guys, meanwhile, take a break. It's now 19. Why don't we take a 3 minutes break? 9:22, okay? Okay, thank you. So,
What's the here, Ibrahim?
you're not here?
Yeah. Oh, sorry. Is this 2160?
No, you're in the wrong class. Sorry, man. Okay, there we go. I don't have a pen. You wanna use a pen maybe from your classmate? Okay, awesome. Thank you.
On the game. It's the 68 minutes.
Okay, 1 more minute, and then we should really resume. All right, let's resume. Okay, yeah. Before we dive into the second example, which is about Fibonacci number, before we do that, yes? I haven't? Oh, thank you. That makes sense. Awesome. Okay. Yeah, so before the second example, we're going to see what the common errors are for recursion. We're going to have 2 examples over here. They are very common. The first one, okay? I want you guys to just mentally try to trace this particular factorial, for example. Do you think this factorial will work? Number one, I can tell you that if you compare this one here with what we just traced before the break, it seems to be shorter. Specifically, we missed this one here. Right? We don't have that. The question is, would it still work? If you don't think that will work, why? Marcus?
Because it's just going to go on infinitely. So if you don't set it equal to 0, then it's going to go into -1.
Uh-huh. Right.
So basically, the base case there, so it'll stop the stack instead of
Absolutely. Absolutely.
stacking colors.
Yes, thank you. So this is actually what we said right before the break. In order for the cost stack to actually stop growing at some point, you definitely need at least one base case. That's principle number one whenever you want to program in recursion. Okay? And for this one here, for example, you guys can just try over on the paper, not on your Eclipse. I don't want your computer to freeze afterwards. If you try factorial 3 over here, and if you just return, it's going to return factorial 2. And then again, it's going to return factorial 1, and then factorial 0. Now, at this point, is it going to stop growing? No, because there's no such condition over here. So it will just keep going to factorial minus 1 all the way to until you will see something called stack overflow exception in Eclipse. Okay? It's a very typical one. Stack overflow exception. Okay? So always put at least one base case. At least one base case. Okay? Example number 2. Let's say, question. At what point? Oh, that's a good question. I think Eclipse actually have some runtime monitor, which will try to see, okay, if I try to execute your recursion, but somehow I found that every time you simply just push onto the step without executing too much, that you can somehow notice at some point. Maybe until you get into maybe about 100 or 200. That's a typical depth of the recursion. In that case, you can tell you got stack overflow exception. Yeah, good question. Very nice. How about the second one? Let's say we do have the base case. And do you think this one is going to work? I'm pretty sure I have a sharp eyes. Pay attention to what's really happening here. We have base case. We also seem to have recursive case. Before I point to you, let me see anyone else notice that. Yeah, you guys are too good, so let's see if anybody else spotted out the difference. Well, I can tell you that what the difference is. Here. But is it going to do something harmful? And what's wrong with this? Go ahead, please.
It's just going to keep multiplying by itself.
Is it ever going to stop? Not really, right? Okay. So this will be another possibility of running into the stack overflow exception. For example, if you got a stack over here, factorial 3, I can tell you what this one is even worse. Because when you get to you just say n multiplied by factorial 3 again. Factorial 3, and all the way indefinitely. That is still, okay, stack overflow example. Overflow exception. And what can we learn from this error? So that means whenever you want to program the recursion, of course, number one, you want to have at least one base case. And number two, whenever you're making a recursive call, you want to make sure you cannot just pass the parameter verbatim. You somehow want to conceptually reduce the size of the problem, at least. Okay? When making a recursive call, make sure to call the method on a strictly smaller input. Strictly smaller input. So the strictly smaller is really the critical point. Okay? Strictly smaller. For example, you might just change this from n to n minus 1. It is strictly smaller than n. Okay? So these are the two common errors. Either you lack the base case or you lack the reduction on problem when you make the recursive call. Okay? Either one. All right, that's the slide here. And this is just about the cost stack, which we just traced before the break. You can definitely read the slides if you still got trouble understanding that. And that's Factorial, okay, good. Fibonacci, okay. Let me present to you the problem over here. So guys, have you seen the Fibonacci sequence before? Maybe from first year? If you haven't, that's okay. Look at the sequence here and tell me what pattern you can observe from the sequence. We'll try to solve that, first of all, define its pattern recursively. Marcus, go ahead.
So it's just the number itself and the number before it added together gives you the number after, and then that pattern just keeps repeating. So in this case, 1 plus 1 equals 2, then 1 plus 2 equals 3, 2 plus 3 equals 5.
Okay. Yeah, for example, you can see 1 plus 1 over here will give you the 2. And 1 plus 2 over here will give you the 3. And also 2 plus 3 here will give you the 5, and etc. Right? But let's be a little bit more careful. Okay? We say the Fibonacci sequence, which is called the F. Okay? This element here is called F1. And this one over here is F2. This one here is F3. And F4. And so on. You can go up to however large you may want to. Okay? Now, we want to somehow define this pattern over here recursively. And how do we do that? We want to think about, again, base cases and also recursive case, right? What would be the base case in this? Meaning that if I give you some f, if I give you some problem f, maybe n over here, how small should n be in order for you to get the answer right away? Okay, when n, excuse me, when n is equal to 1 or 2, I can tell you why visually. Because when in this way, you don't really have any 2 previous number for you to add on. So you just define f1 is always 1. Similarly, for 1 here, you only got 1 previous number, you don't have 2. So that's why you also need to define that directly. But starting from this number over here, you always got at least 2 numbers before that. So you can add them up to get this number. Okay? So we're going to have F1, F2 will be the base cases. F1 will be 1, F2 will be 1. Now, what about Fn? What about this? In the factorial example before, we say in order to solve factorial n, you want to calculate factorial n minus 1. In this one here, similar. Except that, in general, you may want to solve maybe several strictly smaller subproblems before you can get a final solution. How about this one here? It's also quite obvious. Now, go ahead. N minus 1 plus Fibonacci n minus 2. Okay, like that. So, for example, if I want, for example, particular one, if this is Fibonacci of n, I just need to calculate the sum of n minus 1 and n minus 2. Right? It's a very standard definition, right? So just make sure you got this idea. It's also a very simple example. So that will be the recursive design for the solution. And how do we do that in Java? Okay, I'm thinking that I will just give you some very high-level tracing today. I will still need to do the stack tracing, but maybe not today. I'll start you fresh on Wednesday to finish that. For now, let's understand how the Java code should look like, and then how would the high-level execution look like, and then we move on to more example. Okay? Let's take a look. This will be the recursive definition. Okay? So you can see we got 2 base cases. When n is equal to 1, when it is equal to 2, that correspond to 1 and 2 in the Java code. Right? And they simply got 1 and 1. 1 and 1. Right? 1-to-1 correspondence. And what about here? If I want to calculate f of n, which will be the original problem, I should really do n minus 1, which is over here, make it a recursive call. And another one will be, let's see, how about orange? N minus 2. And this will be n minus 2. So think of it as this. So you can think about this one here. Okay? So this will be a solution to a smaller problem. You want to calculate n ultimately, but you want to calculate n minus 1 separately first. And also, this will be the solution to another smaller problem. Solution to another strictly smaller problem. And once you got a solution to each one of them individually, this one here, combine them somehow, and you will get the ultimate solution. Okay, so that's the code. Okay, and how do we trace that very quickly? And to really do on the stack, it might take me about 10 minutes, but I don't want to do that. I'll start you fresh on Wednesday. I'll show you the high-level tracing using a tree. How do I trace Fibonacci of 4? Start with Fibonacci 4 over here. In order to calculate it, it's definitely a base, is 4 a base case or recursive case? Recursive, right? Okay, so that means in order to calculate it, I need to calculate Fibonacci of 4 minus 1, 3, and Fibonacci of 4 minus 2. And now I want to calculate these two before I can get this. To be more precise, I want to plus these two. Before I can get to this one here, evaluation is always from left to right. I need to calculate this one here, right? To calculate that one there, I need to have, that's also not a base case. It's still larger than 2. So it will be Fibonacci of 2 and Fibonacci of 1 plus them. Okay? And now we are good because you can see that the 2 here is a base case, which will give you 1. The 1 here is also a base case, which will give you a 1. Once you say 1 plus 1 is going to give you 2. And then Fibonacci 2 here is again a base case, also 1. 2 plus 1 is going to give you 3. So that's the final answer. Okay? That's basically how you can think at the higher level. But we definitely should also do one more tracing on the stack, maybe on Wednesday. That's what we'll do, not today. Okay? And we got about, maybe about 15 minutes or so. I want to do maybe more example with you about recursion. I want you to get more intuition about how to solve problems recursively. Let's try that. Okay, so when you look at the slides, you will see Fibonacci sequence. That's something we just spoke about. And then there will be another more advanced example I would like you to try as exercise, which will be to trace Fibonacci of 5. And for this one here, once you go over with me about the tracing for Fibonacci of 4 on Wednesday, this one should be straightforward. Okay, but you can see the slide for the full tracing. That's something you can go over maybe after Wednesday's lecture. And then let's now do, okay, let's now do some recursion on Java string. Okay, before that, we need to know about some method, okay, which you may or may not have known. Okay, and this is just some tester to illustrate the method. I want to especially want to show to you how you can use the substring method. Okay, because for the substring method in Java API, you need to pass 2 indices. Okay, but how exactly do you do that, right? Let's go over one example. Let's say you have a string S pointing to A, B, C, D. Okay, so S is pointing to a string A, B, C, D. And Java string is like an array of characters. So over here, you're going to have indices. Index 0, index 1, index 2, index 3. Okay, like that. And let's see how we can manipulate it. The first one, if I say S the substring over here, oh, one thing to say. Whenever you do substring, and then you pass out index I, and also you pass out index J, what does it really mean? That means you want to create a substring in this particular index interval. And maybe from your calculus class, have you seen notation like this? I and also J. Do you know the difference between this and this? Right? This means inclusive. This means exclusive. Right? For example, if I have, for example, from 2 and then 5, how many numbers are there? 2, 3, 4. Do we include 5? No, we don't, right? Exactly, just 3. So that'll be 2, 3, and 4. As long as you understand this idea over here, and this corresponds to the I and J you pass to substring, you're good. Okay? Now, what would this be? This is saying we want to create a substring in 0 inclusive, but also 0 exclusive. What does that mean? That means nothing, right? So this will only give you an empty string. Okay, so this will just be empty string. You can double check. Okay, let's see another example. Let's say we have substring 04. What would that be? Well, 4 here seems to be out of bounds, right? But would that be okay? Yeah, since 4 is exclusive, that means we're only going for 0, 1, 2, all the way to 3 only, not 4. Okay? All right, so this one here is going to be starting from 0, but 4 is exclusive. This is equivalent to from 0 to 3 inclusive. Okay? So this is going to give you the entire string, 0, 1, 2, 3, everything. All right, guys, there's something for you to go over. Substring is actually very useful for our manipulation on the string. All right, for the rest, you can just go over them. Okay? Let's now do as many recursion examples as possible. I got 3. We'll see if we can at least go for 1 or 2. Okay? We got about 10 minutes. Example 1. Do you guys know what a palindrome is? Heard about the term before? Okay, I will define what it is. If you don't know the term, that's okay. The concept is actually rather simple. A palindrome is simply a word that reads the same forwards and backwards. And do you know any example? Madam, yes, madam is a typical one. Race car, yeah. I don't know why. Everybody knows about the race car example. It's here, but okay, that's good. And special case. If you want to program in recursion, always think about what might be the base cases, the simplest one. Is empty string a palindrome? If you read it forward, backwards, the same empty string. So it will be a palindrome. That's a one base case. What about the string with only one character? That's also a palindrome. A and A, right? The same. And madam, as you said, it is a palindrome. M-A-D-A-N from left to right. M-A-D-A-M from right to left, the same. Palindrome. Race car, also palindrome. You can double check. What about this, man? It's not, right? Because M-A-N, N-A-M, they are not the same. Okay? That's the conceptual idea to see, given a string, whether you can judge it's a palindrome or not. And now, we want to say, given an arbitrarily big string, how can you check recursively whether it's a palindrome or not? And of course, based on what you have learned so far, you know how to use a loop to check whether it's a palindrome or not. You can definitely do that as an extra exercise if you want to. But let's now think about how we can do this recursively. Okay? I'll help you a bit. In order to program recursion, think about base cases first. If you're simply given an empty string, as we said, it's going to be true. It is a palindrome. And if you're given a string whose length is simply 1, like an A, that should also be true. But now the question is, what if you got a longer string? How do you solve that in general, recursively? For example, I got different combination here. I got race car. Well, they're not really meaningful words, but just different characters. Apparently, this is a palindrome. This doesn't look like a palindrome. And this one here doesn't also look like a palindrome. But how do we resolve that recursively? Okay. I'll give you guys some visual hints. For those of you who might be new to recursion, I really want you to think a little bit more. Okay. I'll give you some visual hints. Given a string like this, okay, if you just want to scan from left to right using a loop, that's not recursion. You definitely need something that's a little bit more clever. How about this? How about this? These are visual hints to you. So what am I doing here? I'm basically saying, in order for me to figure out if a string is a palindrome, I don't really scan from left to right. I try to look at the beginning character and the rightmost character, try to compare them. Okay. Here, also I look at this and this and this. Okay, and then you can see this part here and this part here. So what do we know? In this case, if the beginning and the end are the same, what does that mean? Does that mean it's guaranteed to be a palindrome? Not guaranteed. It means there's a possibility the string can be a palindrome. In this case, if the beginning and the end, they are not the same, then it's guaranteed they are not palindrome. Because if you try to read from left to right and right to left, this and this are already different. Okay? And for this one here, they are the same. But when you try to look at this particular middle part here, itself is going to give you some violation. Because if you look at here and here, they are not the same. Okay? So to really think about how to figure out a palindrome recursively, this is what you can think. Compare the first and last characters. And there are two cases. Either they are the same or they are not the same. So case one. If they are the same, then you might do something over here. Case number two, if they are different, like in this case. If they are different, that means there's no way they are palindrome. That means not palindrome. Now the question is, how can we describe this part over here? Let's say in this case over here, they are the same. In this case here, they are the same. What should we do to move on with the computation?
We need to take the substring of the word without the first and last letter.
And
So substring of 1 and then the length.
Okay, I agree. So we definitely need to take the string without the first and the last. What do we do with it?
Do it again.
What do you mean do it again?
Check the first and last letter.
Yes. Okay, so basically, in order to check to see if this string here is a palindrome, I need to know, number one, whether the first and last characters are the same, and also if the middle part without the first and last is also itself a palindrome. So this will be a sub-problem that's actually strictly smaller. Okay? So let's say, just for example, let's say this one here. I'll say palin over here. If I want to know if this string over here, ARACECARS, I want to know this original problem solution, but it might be too big for me. So what I do is I will take the beginning and the end character. And then I would say this can be defined by the A here, the beginning, and also the end, which is S. And also, in order for the entire string to be palindrome, number one, beginning and the end must be the same. Number two, the middle string over here must be a palindrome itself. So this is a critical part, which is about what you said to calculate the substring. So this would be palindrome of RACECAR. Okay, over here. And you can think about this part over here is a strictly smaller problem. Okay, so just for this one here, ultimately we can see that this is race car itself is a palindrome. That's not enough because the beginning and the end character here is not the same. So overall, it's not a palindrome. Right? Both conditions must be satisfied. That's why we're using the ampersand, the conjunction. Let's take a look at the Java code very quickly. I think we just got enough time today just for this one here. And for Wednesday, I'm going to do 2 more on the string, and then we'll move on to how to do recursion on the array. Okay, that'll be the plan. And we should be able to finish almost everything on the recursion on Wednesday. There might be some small bits we have to finish on Monday, and then we are done. Okay, so here is Palindrome over here. That's a Java method. Okay, and we simply got an arbitrary string. And these two are the base cases. Either we got empty string, or we got a string with only one single character, right? So these are the base cases. Empty string, or a string of length 1. That means you can calculate right away. Right? That's the base case, this part over here. And what about the else part? This will be the recursive case. Okay? So now let's see this. If you think about this is the word, which is a string. And think about a string is an array of character, right? So index 0, index 1, index 2, all the way to, now, what would be the maximum index you can use to access a string? Length minus 1, right? And, for your information, you can also use the length, but word.length, be very careful. Now, since the word is a string, if you want to calculate its length, it's a method call, so make sure you put this. All right? If you didn't put it, it's going to be error. Okay? And the idea would be we want to make sure this character here is the same as this character. And also, what's in the middle over here itself is a palindrome. And how do we calculate the middle? As Jasmine just said, we should use the substring. Word.substring over here, starting from 1, and then what should I put over here, guys? Should I just put word.length minus 2? Word.length minus 1, right? Because we don't want to include this one here. Word.length minus 1, right? That's a conceptual idea. Let's just double check. Right? First character, last character, and the middle would be this one here, right? That's exactly what I just went over. And then you want to say it is a palindrome if first character the same as last character, and also the middle part is also a palindrome. So this is really a recursive call. Final remark. So this is really a recursive call on a strictly smaller problem. Strictly smaller problem. All right, any question about this? Okay, so what can you do before Wednesday if you want to do some exercise on recursion? The lab is going to be released after Wednesday's class. But if you really want, you can go back to that site about coding bat. You can definitely start with recursion 1. I think there are many problems you can start solving already. So for the final exam, we'll only test you maybe questions around the same similar difficulty level that we cover in the class. And for many of them, you can definitely find exercises on the coding bat. Right? For this extra exercise, it will be up to you. All right, you have no question here. I'll see you tomorrow, Tuesday, and then good luck.